So, welcome to the webinar series by IITACB, IT Alumni Center, Bangalore. So, for the new audience, as you know that the IITACB is a unique center providing networking platform to establish the collaboration between academia and industries through the project of course, the national importance. So, in today's webinar, we have two speakers. We'll be talking about sustainable AI cloud. And so the first speaker is Mr. Srinivas Varadarajan. He is a CEO and the founder of Vigyanlabs, which is a startup that provides an innovative solutions for energy management, climate change, micro data centers, and also the green data centers. So he has over 30 years of experience in this IT industry and has multiple patents in energy management and middleware products. He also served as the principal architect of Aadhaar. So he's on a mission to help business achieve a sustainable digital transformation through this Vigyanlabs, which he has founded. And our second speaker is Mr. Narasimha Nagabhushan. So he has obtained his master's degree in mechanical engineering from Colorado State University after he finished his BS from Mysuru. And so he is a certified measurement verification professional from the Association of Energy Engineers and ICER certified engineer professionals. And he began his career at the NAL, National Aerospace Laboratory, Bangalore, as a design engineer. And he has contributed largely to Hansa and Saras aircraft programs by NAL. And so he also founded, he's in 2020, he co-founded Rachana Enercare Group with along with Mr. Anil Kumar Nadiger, and where he basically this provides a service in engine energy efficient power quality management and sustainability. So both the talks will be moderated by Mr. Nitin. So about Mr. Nitin, he holds MTech degree from in computer science and engineering from IIT Bombay, and currently he's a technology and enterprise architect with the Department of Post, leading to IT 2.0 modernization initiatives. So formerly the worldwide engineering lead at Walmart Technology, he also specialized in designing, building large-scale retail platforms, competitive analytics, and he also contributed to India's Aadhaar UID biometric-based registration and deduplication program. And he guides organizations in enterprise architect, leveraging AI analytics and modern technology for sustained results. So we have three wonderful people from very specific, the AI programs, and we are going to really have a very knowledgeable conversation with them. And today's webinar is co-hosted by Dr. Sushila Venkatraman and myself. And for audience, please post your questions on Q&A box, and that will be taken up during the discussion by the talk webinars moderator. So over to Nathan.
Thank you, Professor. Very kind of you for those introductions. So sustainability, data centers, and add to that mix AI is definitely an interesting perspective for all of us. And there's a lot of advancements happening. We hear some stories and the news every single day. So Srini, I'm kind of associated with your work. I have seen your paper on micro data centers along with a lot of people. So when I heard or saw the word inverse hyperscaler, I was pretty intrigued by what does that word mean. And so especially in Indian parlance with a lot of your customers. So if you could help us kind of understand that, what do you mean by that, and how is it relevant for the kind of things we are doing in India?
Yeah, just a couple of things to add, right? India as a country, we always had constraints, right? We always grew up with constraints. We do still have constraints in many things, right? In terms of resources, okay? We are with 1.4 billion people and a limited land mass. I think historically we always grew up with constraints. See, so land is always a constraint. Yes, we have limited land compared to other countries. There's number of people per square kilometer is much higher density of this thing. Water is scarce. We always have water issues. Then power. We always have. Till today, we have power cuts. That's why every house has a water, sump for storing water. There's also UPS everywhere. So these are the three resources are constrained. So and when you look at looking at the approach as a country, right? Today we do have solar rooftops. We have distributed grid, right? Everybody has there's a solar rooftop program from the government. Subsidies, we do net metering. We can generate. You can be a generator and consumer energy. Energy is using solar is fairly distributed. Then to look at the hyperscaler approach has been to build large scale infrastructure, centralize everything. So which means you need centralized power, a lot of energy one place, available at one place, lot of water or close to water source. You need a huge amount of land. So we look at the inverse, means why can't we do differently? Because knowing the constraints, we don't have a large tracts of land. Land is very expensive in the country. Can you do with less amount of land, little or zero water? Can you with less energy? We are a country blessed with a lot of plenty of solar energy. Can we use renewable energy and also at the same time minimize energy usage? So inverse in the sense is like can you do something differently, which exactly suits our geography, economics, and of course the current GDP and the requirements. So that's where the word inverse came in, right?
Right. Yeah, very interesting. Very interesting. And it kind of resonates with the requirements you see in the market, either from the government or the small organizations and stuff like that, right?
Yes, very much. Many organizations. So we never had a large scale infrastructure in the country to start with. Right, we had limited infrastructure. Being such a large distributed country, right? The only thing which has spread across the country is the mobile, right? Mobile phones, pretty much there. There are towers everywhere. Other than the broadband penetration is still low, the network penetration is low. We want to offer, new services like AI coming in, new services. We don't have very large backbone in the country. The only way is to build a lot of small things and offer at the edge, at the taluka level, at the district level, or a Hobli level, right? The people decide, right? Today, with the mobile and apps coming in, people don't worry about what is there behind. As long as they can, the convenience, right? The mobiles of the world provide apps for the convenience. But what is there to serve them, right? So I think if we can prevail infrastructure which can work, which are closer to the users, which can sustainable use the local energy grid, right? Or the solar energy and solve the last mile problem, right? We don't have a large high bandwidth backbone. So we try to solve multiple problems at the same time, right?
Correct. And obviously, reflecting on the visit we had on your, data center, it's completely different way of thinking, right? From hyperscaler.
Yes.
How you look at hyperscaler versus how you look at the micro data centers or the inverse of the hyperscalers, right?
Yeah.
And you have alluded to a few of them. So maybe it's right time for you to probably, start with the presentation and also highlight some of the concepts which you have.
Yeah. Let me just briefly talk about, quickly, and you can interrupt me in case, want me to stop in the middle. Okay. Basically, if you look at, if you want to build a cloud, what we call the AI cloud, what are the requirements, right? What are the things you need? You need a data center. What is a data center? It's a building, right? It's building. The building requires land. You need power, right? Power infrastructure. You need transformers, you need a grid, or it could be solar power. They need what energy, right? Energy for cooling. You need something to cool the equipment, need energy and water. Next part is the IT physical infrastructure. You need compute, CPU and GPU. You need storage. You need network devices. And to make all these things work, you need quite a bit of software. So in the cloud, you offer infrastructure as a service, platform as a service, AI as a service. You need all these three things. These are the requirements. And what are the challenges we face today? Unfortunately, today, everything works in a silo. Because a building is built by a civil engineer, right? You have a set of people who build the building, right? You just tell them, I want to put, a tier 3 data center. I want 100 racks. There's a standard, TI 942 standard, which gives the specifications. How many square feet of white space you need to build, and so on, right? They build the building according to specification. They do the bob and go. It's fine. Then you have the electrical engineering coming in. They will just tell you how many kilowatts or megawatts of power you need per rack. They look at your requirements and say, okay, you need so much of UPS, you need so many, so much of UPS, generator, transformer, or solar, right? They will come up and they'll put the power. There's a standard formula. Okay. The typical assumption is, you have a 100 watts of IT load. You need to convert that to the cooling load, right? So you just use the 100 watts, 100 kilowatts divided by 3.84. They'll say, okay, you need about 30 tons of, 25 to 30 tons of chiller. Okay, you put the capacity there. So typically people use water-based cooling. Then comes the IT infra. Okay, IT infra, it's done by a set of people. Look at, how many servers you want, how many CPUs you want, how many RAM, much of RAM you want. So you want to configure the CPUs, servers, and then they design network, right? Network elements, storage network, and then of course AI GPU. How many GPUs you want? You want H100 cluster, S200 cluster, people put together. And there you have three different teams doing different things. And there are three different bits and pieces of software. There's a BMS system, the building management system, which looks at the building electrical part, right? Building part of it, automate the building, the sensors in the building to look at the building, access control, cameras, and a couple of things, right? Then the DCM looks at a bit of the power and the cooling, a little bit of the server, right? Server part. Then the IT infrastructure, you have the cloud management software, which is the IaaS, PaaS, and the AF service. And on top of it, everything is a users, right? People build AI applications, legacy applications. So you have sort of silos, and each of the teams work differently, right? Each of them have their own objective. They try to optimize in their own part, right? The building will try to optimize for, building cost, space, and so on. The power and cooling will try to do on their own, the standards. IT infra look at the one, and then there's application vendor. Application just consumes it, right? Application guy doesn't understand, doesn't want to understand. I just need so much of CPU and RAM storage, that's it. Give me, I'll just use it, right? So these are the challenges today because people operate in silos. Then what we try to do, right? If you want to solve, say having built Aadhaar and many other projects, what we found is there's no magic bullet. There's no one big thing to do everything, solve all the problem. Okay, we said you need to look at a holistic approach and you do n number of things, small little things, many of them, to put together to solve this energy problem. And what have we done? What did we do, right? Try to do. So we have to set up some goals and objectives, right? If you have to achieve the whole thing, you need to set up goals. First of the goals is reduce the usage of land, because land is sparse. We have, data centers coming up in metros. It's tens of thousands of rupees per square feet, right? That's a lot of money to save the land. So can you minimize the land usage? Can you minimize energy usage? Can you reduce the element water usage? That's one goal. Next goal was, PUE. Can you achieve a power utilization efficiency of less than 0.3? One. Third is about, while you're doing all these things, you have to enhance reliability, availability, and security, because you cannot compromise, right? You can't say I'm efficient but not reliable, not secure. You can't compromise, because people come to cloud or data centers because they want high reliability and security. Finally, nobody wants to spend more to achieve something, right? You have to reduce the cost. Is it possible, right? These are four, different pillars we had to work on, and each of them there's a hell of a lot of work you have to do in each area to achieve those goals. Go to the next slide. Just tell you what all we had to do, right? There's a lot of things to do. Let me look at the various small blocks, like the four pillars we talked about. The building. So we look at the way traditional building is built. You use a lot of cement and steel, right? So can we reduce the usage of cement? Can we make the building naturally cool? If we looked at some of the old Indian ancient buildings, we found that there is techniques people use our ancestors probably in the hundreds of years back, with no electricity, they use special material to keep the buildings cool. So we just studied that, and I got lucky to work with a couple of good civil engineers, architects, who design special bricks. So we created special bricks, build the building. What happened is, because we use special bricks, and they reduce the cement usage by almost 70%. These bricks that keep the building naturally cool by almost 60 degrees centigrade, which means your cooling load on the building reduced naturally. Next, we did a lot of redesign. All the building data centers had false ceiling. I said, why do you need false ceiling? We found, okay, you do the design differently. Example, false ceiling is there to conceal the wires and trays and all. Can we cast those pipes, sensors in the roof itself? So we cast the roof. That way you eliminate the false ceiling. Same time you also reduce the 1 feet, right, height. Reduce 1 feet height. Then we eliminate switches. Okay, again, wiring switches, to reduce copper and wiring switches. We eliminate switches. All this helped. Having a special civil infrastructure help us to reduce the, of course, the building, make the building more sustainable, eliminate a lot of wastages, right? So on. Next part was the cooling part, right? Cooling part, it was clear from day one that we should not use water, because we are a water-starved country. We always have water constraints. Can we use air-cooled chiller? But when we started using air-cooled chiller, we found, we got the best in the market. When we built the data center and went live, we found that, the PE was 2.0. We were shocked, actually. Then we have to work with the chiller vendors, ask them to give us the APIs. And we said, why can't we use AI? And we built a AI-based closed loop control system, which actually controls the chiller in real time, right? Based on the server load and thermal footprint, controls them in real time. Using that automation, we were able to reduce the PV from 2.0 to less than 1.3. So that automation of the chiller helped us. In addition, we had to do a lot of things, the energy getting lost in the data center to achieve the PV 1 watt. Just chiller is not just the one part. We have to look at, we have to look at every component, right? Transformer. Found people the traditional transformers use were not very efficient. They also occupy a lot of space and cost points. So I went back to my prof in the college. Okay, I told him, we are building a data center. Can we relook at the fundamental principles? He said, okay, spend a lot of time with the Professor Nagaraj to help us, redesign a new transformer, which is highly energy efficient. Luckily, he had one of the students. He told the student, okay, we're going to build a transformer for my another student. So luckily, we are lucky to have one of the manufacturers, a student of my prof, who agreed to work with us and design a custom transformer. The transformer actually is, the size is half of the conventional transformer. We reduce the space, and of course, it doesn't cause any humming noise. It's highly energy efficient. Losses are very low compared to other ones. Next part of the electrical panels, right? So we look at the panels because panels can redesign the electrical panels itself. With a lot of instrumentation here. Because one of the things we found in the data center was energy losses happen. People get auditors to come and plug in a PQA meter and try to analyze. Can we design special equipment, sensors and or power quality analyzers built into the electrical panel, which is AI, which can actually learn the usage of electricity, right? Various parameters like current, voltage, harmonics, power factor, n number of parameters. Can it measure all these parameters in real time and use predictive analytics and to identify anomaly detection, to identify faults, potential faults, energy leakages. So that helps us to identify the leakages and faults. They eliminated the bus bars, redesigned everything. We found efficient. Like this, we did a lot of little small things across the board. Then finally, not about is the IT equipment, right? We found all the IT equipment do consume a lot of energy. So we looked at to talk to the vendors and got probably the most energy efficient equipment. At the same time, we said the work done was not proportional to the energy being used. So why can't we use AI to understand the workload pattern? Because in a cloud, the workload is not constant. There's a spiky, busty traffic, right? It goes up and down. We also found idle times, the energy consumption is very high. Can you use agentic AI there to learn the energy usage pattern, predict the usage of every device? Could be storage device, could be network device, could be computing device. When you look at that and predict the usage and optimize the energy in terms of maybe reducing the clock speed, turning off something. So there's a lot of things to do engineering. We did that. These are the 4 pillars we worked on, reducing the energy usage, right? The building, the cooling, electrical systems, then of course the IT equipment. Additionally, we had to do a lot of new equipments. We found the traditional BMS takes about 15 kilowatt. People end up putting a rack for BMS. So when we talk about energy efficiency, we don't have the luxury to spend 15 kilowatts. So we actually ended up building a IoT device. Also, this was not our goal. We wanted to make energy efficient device. We built a small box, which is actually size of your mobile device, slightly bigger than mobile device. 15 watts, it powers the whole data center. Yes, I talked earlier, we actually put agent on server every device, which can optimize the energy usage. And we have to actually build the entire cloud management stack. Because we have to, how do you orchestrate, I said, there's a silos, BMS, we have DCM and many things. So how do you, integrate everything together so that you can orchestrate things and control and manage everything? So we built our, again, AI stack. So along with that stack, we actually built our own homegrown AI engine called as a power mind because it does a lot of things on power. Sort of, I would say, agentic AI sits on every device. The device doesn't have any, you can't, for example, chiller, I can't put anything. Chiller vendors don't allow to put anything. We put on a BMS, right? Put on a edge device. Either we put the agent on every device or on a proxy, right? A proxy where you put that control. So that's how our power mind is like a small C++ code, highly optimized. It's about 3 MB of file. It's very, very small. You can run a small device like a smartphone to a server. It just occupies minimal energy. It does basically the agentic AI works on every device. All the AI we use to run our data center is not easy. We are very clear. We are going to use talk about energy efficiency. We can't afford to use an energy expensive device, right? That should be very, very clear. What is in the background in this picture is the data center, right? We see the red is a red bricks, right? On the rooftop, we have a solar. A lot of. we're gracious to have some of the smart architects in Bangalore to come and help us in terms of setting the windows, the painting, every aspect. We'll look into it from the energy perspective. Yeah. I hope, Nitin, I've been able to answer your question so far, right? Yeah.
Yes, absolutely. Absolutely. This is pretty intriguing. And when you said BMS, maybe that term wasn't introduced.
Sorry about that. So
Yeah, no worries. You want to take a water break?
we're just talking about a building management system, right?
Building management, overall
Yeah.
building management
Yes,
system.
yes, yes,
Understood. Yeah. And yeah, absolutely. And I've seen it in real. One question typically people ask you have done this because the data center was a micro, like, sub gigawatt or sub megawatt kind of data centers. Will these concepts be applicable for megawatt or a larger hyperscale kind of things?
The approach has been to create a modern data center, right?
Mhm.
Apply these principles, and you can. So the approach is scalable, right? Literally.
Right.
Look at today. We started with 5 racks.
Mhm.
We achieved the PV 1.3. We
Right.
said let us double. Work.
Okay. Got it.
We put 10 racks. Now we got 40 racks. We kept on adding racks in a modular way. Still, we were
Mhm.
able to maintain the energy efficiency and the PV till now.
Mhm. Right, right. So the same thing, whatever you have done on the kilowatt scale can be,
Yeah, can be scaled up linearly. Yeah.
can be scaled up and modularly, to be
Yeah,
precise, like,
that's right.
not necessarily, understood. Yeah. So going back to your, yeah, Shane, you want to take a water break?
Sorry.
Yeah, no worries.
Yeah, please. Yeah, go ahead.
Yeah, yeah. So 4 themes we talked about in your presentation, right? One is definitely how do you we covered some of the aspects about the optimization in this itself. What do we need to optimize? Secondly, no water at all in the cooling. And the third thing was usage of the right material so that even in the environment and the ecosystem is like, overall sustainable, right? And fourth is, though we are building data centers for AI, you have used AI within, like, for AI and with the AI, right? So those kind of things. So if you could just highlight on that AI aspect of it, because this has been a journey. I know you have built that Mysore.ai as well. I mean, you have contributed to that. What aspects of AI have you kind of used in that effectively?
Basically, if you look at today in the data center, right, what are the things you need, right? Look at the various aspects of the data center part. Let me look at the computing part, right? Computing itself, right? Computing itself.
Mhm, mhm,
So basically, we have a deep, ML model, the neural network. We hand
mhm,
code C++ code, neural network, because number of parameters you identify the server utilization is not trivial.
mhm, mhm, mhm,
It's not trivial. Just can't look at CPU utilization. The CPU, memory, network, IO ops. There's a connections, and number of parameters are there. You have to create a model which
mhm,
understands these parameters, right, and predicts that one.
mhm.
Today's e-commerce load, everything is spiky, right? I can't react,
Yes.
operate in milliseconds, right? So this is why
Right.
so the agent had to be, you can't use a traditional model of, inference model. Doesn't work because you have to you don't have, that luxury of time to react. So we
Mhm,
had to build autonomous agent, sits on every device, the server, example
mhm,
server, right? At the host level, sits at the
mhm,
host level, understands and reacts in milliseconds, right? Reacts, you can't afford. Okay.
mhm, mhm,
So that's where we applied ML model,
mhm,
predict the load pattern.
mhm,
Based on the pattern, is the next minute is the server going to be idle, is going to be busy, or traffic
mhm,
pattern? Then take some decision, right? Like could be turn off a core, reduce the
mhm,
clock speed, many things we
mhm.
do, right? Or could be in a governor,
Correct.
many parameters
Right.
available, again, depending on the operating system and the hardware. You
Right.
need to understand the capabilities of the hardware because we have Intel, AMD, and ARM, so many kinds of hardware, so many kinds of operating
Mhm,
systems. You need to understand its vagaries and take
mhm,
what are the capabilities of the hardware and predict and take
mhm.
action and in real time, right?
Right.
That's
Right.
one part of
Right.
it.
Mhm.
That's one part of we did apply model, right?
Right.
Second was the electrical part.
Mhm,
Electrical part, is basically to identify energy losses and prevent failures. So
Understood.
where we basically use anomaly detection to identify it, because what we find is many often electrical systems fail, right? And then it's very hard to bring it back. How do you prevent failures? By predictive analytics or anomaly detection. So look at could be a harmonics issue, could be because of one faulty equipment can cause a harmonics issue. So we use the anomaly detection to identify electrical faults and energy leakages and identify leakages, right? So leakages happen because just look at example, IT equipment is all single phase, right? Single phase. The data center, the electrical sources, UPS are 3-phase. So basically, what the IT folks will do is end up plugging a server into a rack. Just find the free slot, free PDU, just plug it in.
Correct.
PD level, put AI again to identify anomaly detection, then help with prediction and data to balance the load, right? When you do phase balancing properly, you eliminate losses. Harmonics, identify energy leakage. So this was one. Third part is about the cooling part. Cooling is a lot more complex. Because we cannot, a traditional approach has been to look at the return air temperature and control your settings. Here we have, you can't put a sensor in every rack. That's what people have been using, you put a couple of sensors, 2, 3 in the rack and front and the back. So what needs to be cooled is not the rack. What needs to cool the equipment inside. So you need to look at CPU, various, active devices, CPU, memory, disk, and so on, right? You need to look at are they operating in the thermal zone, safe zone or not. If not, you need to have enough cooling, right? So basically, again, we use a neural network and ML model, model their workload, thermal load, right? Thermal footprint of the equipment, right? The rack, and control the chillers, right? It's a closed loop control system. These are probably 3 different areas we applied AI to actually do the automation, right?
Absolutely. Very good. Yeah. So Srini, based on this, is there any other point you want to highlight even in more details?
Probably, I'll just talk about some of the results, right? What have we achieved, right? And
sure.
achieved can give us a fair idea. How much does this efficiency lead into, right? What's the benefits people will just give benefits, right? The numbers. Just look at the number, right? The PUE and the energy consumption, right? Got the total power consumed, IT load and the non-IT load. So just give a number, right? How many devices we have? So we have about 160 devices as of today. I just counted the number for a good data. 160 devices. Servers, pretty much majority is a servers, right? Because everything is a server for us today. The software data. 160 devices consuming only 25 kilowatt of load. The load varies a little bit here and there. 25 kilowatts of load. That's it, right?
Right.
On
And
average,
the PUE is also within the range of 1.3, less than 1.3.
Yeah. So that's what it is, right? We just have, average energy consumption per device is less than 200 watts, right? I would say that actually, if you look at, divide by 25,000 by the 160 devices, roughly around just less than, for 160, right? So average energy consumption per device is 160. So we have device consuming 80 watts, high-end GPUs, probably a kilowatt plus, right? So with the optimization of the, agentic AI and every device, that's how we're able to bring down the energy footprint per device. Once you bring down the energy footprint per device, cooling load reduces. Of course, we use AI for cooling. That's what you said. The chiller load is very, very minuscule, right? It's slightly higher than a home air conditioner, right? Although we have, tons of chillers available, capacity available, because of AI, chillers, don't run all the time. So chiller compressor cuts off, the fan speed reduces. That's how we're able to cut down the energy consumption drastically, right? Next, I just want to talk about the impact, right? What is the impact it has done, right? Across the measure. How do you measure, right? Okay, of course, energy consumption is very, very low. What's the impact till now? It's not today's, it's over a cumulative energy impact. Total energy saved is about almost 2000 gigawatt hour. Water saved is reduction, right? Because today we had to wait to use a water cooled chiller, right? We would have consumed 5 million liters per year. We said about 5 years, about 25 million liters. Was the impact of environment, right? In terms of energy saving, right? It's almost about 38 billion trees sequestered per year. It's like growing a very large forest, right? Yeah. So that's all, I think it's all I had to share. Yeah.
So Shini, we have a couple of questions from the audience. One is, do you have any interesting pictures of these innovations, whether it is a brick or any transformation or a cooling equipment If you have them, if you could show them in the presentation. And second, slightly even maybe you could answer it while you're searching for those pictures, is that PUE, does it vary during the season's year? And like, let's say in the peak summer, or is there any peak for that matter, whether it's a summer or winter?
Yeah, let me tell the summer it varies. It hits about in the peak summer it about 1.35.
1.35.
Winter at nights we run about 1.05 because your outdoor units don't get hot cool naturally, right? And also we also use natural air cooling, adiabatic air cooling. We have built a system in a closed loop control system. Outside temperature is low. We take the outside air and defiltrate it, dehumidify it, and use it for cooling. So this way, so at 1.35 or close to 1.4 peak we have hit. But on average, 1.05 or something is the lowest we have gone. Average is less than around 1.3 or less.
1.2 or so.
Yeah.
Understood. Yeah.
Excuse me, try to dig up a slide. May not have.
Sure. Yeah. And another question coming while probably you're searching for those pictures.
I think I got the picture. I'll just show you the picture right away.
Perfect. So we'll wait for the next
question.
question.
I'll just show you the building picture. Okay.
Fantastic. Yeah.
Not have all the pictures.
No
Anybody
problem.
please reach out to me. I'll share the picture separately.
Yes. So maybe as a follow-up, we can do that. Yeah.
This is the building, right? Can you see the building, right? Rooftop solar, and then you are right completely built.
And the bricks are specialized, you said, right?
Like
the
bricks,
red
yes,
bricks.
yeah.
Understood.
Actually, you can see on Google Maps, you can see the building actually. Exactly. You can see that.
Good. Yeah.
Okay, let me stop sharing. Yeah.
And Shini, while we're on that topic, there's one more question from the audience, Dr. Srinivas Gorur. Is there any fear of outside air pollution impacting the server chemistry, whether it's a polluting, reacting with the motherboard, or any such phenomena for that matter?
We also measure, we have sensors to measure particulate matter. I got a particulate matter, smoke. We have got quite a set of sensors. So we measure the air quality, we measure the AQI. What happens in an area where you have, a lot of sulfuric acid in areas. I've seen earlier in Mumbai, when many centers are located close to a factory. Some of this sulfuric acid can come in the air and pollute corrode your PCB, right? You have the copper, right? Copper in everywhere. Copper sulfate gets formed. So we need to have sensors to measure the quality, dust particles. Pretty much we have put a lot of sensors to measure all the parameters and take action. Actually, even if we have a PM 1.0 filter, actually, we don't even allow a particulate matter to get inside the server.
Understood. Right. And that will suitably have to be reflected in some of the adjustments which you're doing AI based.
Yes.
Or otherwise, right? Yeah.
Yes.
Understood. Good. Thank you so much. Yes. Thank you. So now we're at a stage where, we have taken a few questions from the audience. We have covered the 4 topics which we have slated to do. And potentially now it's a good segue to start with the next presentation. Again, related, we had so far, I mean, at least personally, I had heard only about, innovations in HVAC and cooling. But now, Narasimha, you have pretty much hands-on experience in all that. So looking forward to, listening straight from you. Over to you.
Sure.
Yeah.
Sure. Good afternoon. Let me start sharing my presentation. So energy efficient data center cooling. So the basic question here is like, do we need to be energy efficient at the first place? Now, as Srinivas was telling that India per se is a constrained country. We have a huge population and our natural resources are very limited. So it is not a good practice to waste anything. So to make the efficient use of existing resources, especially in the energy domain, it makes really good sense as a country to be energy efficient. And because of the huge population base, we have the propagation of smartphones and computing devices. The data being generated is also huge. So the data centers being used to store that data is also very much big or hyperscale or anything like that. So the cooling that efficiently is the what I think is one of the most predominant challenges of today. Now, to give some statistics, approximately around 30 to 40% of energy used inside a data center is used for cooling alone. Now, in India, data centers consume approximately now 1% of total national power generation, which is in the grand scheme of the things, statistically, this shows very, but in absolute terms, 13 terawatt hours of electricity is annually being used of the total 1824 terawatt being generated. This is all sources of energy, like whether it is maybe coal generation, considering that this propagation of smartphones and various computing devices, the amount of energy that is being consumed for data centers operation is expected to be 2.5% by 2030. So the energy usage increase directly translate into increased operational costs, significant also significant environmental impact. So if the considering that the data centers require quality power, and if that quality power has to come from fossil fuels, then there is a significant impact on the environment. So then there are some other options like using solar energy, using battery technologies, storage technologies, and all these things, but they are pretty much like not in the reliable as any base energy generation such as fossil fuels or nuclear or even hydroelectric power. So for one of the easiest and cheapest ways of providing a clean energy and a reliable energy is being more energy efficient. Now, as Srinivas sir was mentioning, one of the critical factors inside in a data center energy usage is what is called as power usage effect. So the power usage effect is generally defined as the ratio of the total facility energy to what the IT equipments are using. So as the lower the power energy effectiveness means the energy efficiency of the data center is more. So these are the more sources of heat inside the data center. The major source of heat inside the data center will be server equipment. Some of the equipments which will be supporting the proper and smooth operation of servers are UPS and PDU infrastructure. But along with that, since they are also having electronic equipments, they will also be generating heat. Network hardware may be minimal heat, but it will also generate heat. Lighting off late, since with major propagation of LEDs, the lighting heat generation is at the best considered minimal. Building envelope and air leakage. This is critical because the data center, if it is having any of its periphery, if any of its boundaries exposed to outside, then it should be properly sealed. Or the data center should have enough buffer in between the wall and the server such that any heat will not be infiltrated into the data center. So if this heat is infiltrated into the data center, that creates an artificial load, and that will be an extra load on the cooling. Now, human activity. Human activity is unavoidable to an extent because the reliability of the data center is critical. So somebody has to come and keep on looking something if something has gone wrong or if something is going correctly or something like that. Now, as Srinivas sir was telling that with AI-based monitoring, everything can be done online, or everything the AI algorithms will do, but some kind of human activity and human interference will be required. So this also adds into the data center heat source. Okay. Now, what are the various types of cooling systems that are used basically in data centers? Now, air-cooled systems, CRA units, free cooling. Now, what are air-cooled systems? The cooling medium inside the data center is air. The cooled air from an air conditioning unit is supplied into the data center, and that cool air absorbs the heat generated by the servers or all other equipments, as we saw in the previous slides, and that that air gets heated up, and that the heated air will conditioned again going back into the air conditioning units. So that is what it means by air cooled systems. Liquid cooled systems, this is one of the latest technologies available where the cooling is supplied directly onto the chip. And that also the other method is where the servers are directly immersed in a dielectric liquid. So the cooling here is achieved through liquid and it is applicable directly. There is no air between the cooling equipment required and the cooling supply. So it is directly done by liquids. That's why it's called liquid cooling system. Hybrid cooling system, it is like it is also, it is a combination of liquid and air cooling, where the chilled liquid is supplied to a heat exchanger at the server rack level. And that server rack level, the air inside air circulating inside that server rack is cooled. So that's why it is called as a hybrid cooling system. Evaporative cooling is again, it's a hybrid cooling system. Is water is used to cool the air where it may come in direct contact with the water. Our air is not direct, air may not directly come in contact with the water. So it is based on, during the further slides, I will explain what is a direct evaporative cooling and indirect evaporative cooling. Now, what are the standards which are used to define the cooling, which are used to define the cooling system of a data center? ASHRAE Technical Committee 9.9 is one of the prominent authorities which provides guidelines for designing cooling for mission critical facilities. Like one of them is data centers, clean spaces, and also some of the electronic equipments. The primary purpose is such that we have a common standards across the board for cooling, designing cooling for data centers and critical facilities, so that there will be the equipment interoperability will be ensured, so that one manufacturer may use something, the other manufacturer may not be using something. So when we want to use interoperably one equipment from one manufacturer, another equipment from manufacturer, we should be able to mix and match things. So that is one of the basic purposes of this technical committee coming up with standards. Now, what are the key concepts this technical committee has proposed? Now, some of the key concepts is there are some temperatures and humidity levels inside the data center needs to be regulated. Even though for some places like in Mysore, we are very fortunate to have very moderate climate. So we can use the outside air as it is, condition as it is, and supply into the data center. But there are some coastal areas like Mumbai, Chennai, and all, where the humidity level is very high. So the humidity has to be reduced. So actually, Technical Committee TC 9.9 recommends what should be the maximum and what should be the allowable range within the data center, both in temperatures and humidity. Because higher humidity will condense at some point of time and it may create short circuits and electrical hazards. And very dry air sometimes will create statics, which may, since the servers have very sensitive electronics, that may damage the equipment in some way or the other. Now, along for the liquid cooling with chat GPT, with so much graphic processing happening, the committee is increasingly focused on promoting the liquid cooling. With all the technology improvements in liquid cooling, direct to chip cooling, and everything, still one of the primary source of cooling inside the data centers is still air cooling. So nowadays, with the increased cooling and increasing level of pollutions and particle level matters in the atmospheric air, the committee is more concentrating towards liquid cooling. Now, based on what factors we select a cooling strategy? Of course, one is server density. So if all the racks in the server are in the server rack is populated with servers, and there are many servers, and within the very small confined space, the heat density will be more. So with the heat density being more, then the cooling capacity will be more. So that depends on whether we go for hybrid cooling or air cooling or liquid cooling. Second one is location. So as I was mentioning, like in Mysore, we are fortunate to have a very moderate climate where our temperature and humidity will always be within the permissible limit. we can go for a lot of free cooling. So, but in vast majority of places where some kind of conditioning has to be done, like you need to reduce the humidity or you need to reduce the dry bulb temperature and all. So like location also plays a very important role. And based on the server density and the heat being generated by, the energy efficiency of the system can be decided by what kind of cooling is required. The difference between a crack unit and a craw unit is like the cooling medium. In craw unit, the chilled water is supplied to the heat exchangers, whereas crack units, it's a direct expansion units. So when the server density is high, when the heat load is high, chilled water is a much better option. So the craw units are generally preferred, and liquid systems will be more efficient based on again whether the technology is available and whether the technology is affordable and whether it can be implemented at that particular place for the given load. Okay. So how can you achieve cooling by energy efficiently and without compromising on the performance? The first strategy we can use airflow management. So what happens is like the cold conditioned air coming from an AC unit can gain temperature or should gain temperature inside the data center only by passing through the servers and absorbing the heat in those servers. If the cold air passes through gaps or if your cold air just escapes through some places where it is not supposed to be and mixes with the return air temperature, then the amount of energy used for cooling is wasted. So that's why the one of the strategies in the airflow management is hot or cold air containment. So once you install a containment, the cold air cannot escape through gaps or anything like that, and it has to pass through servers only. In the server racks, if at all there is gaps, those gaps need to be closed using blanking panels. So the conditioned air being supplied into the data center only has to pass through the servers to gain temperature and cool the servers, and then it has to supply it back to the units to recondition it. So the hot air cold air containment is a very critical, and it is also one of the easiest way to improve the airflow management in the data center and achieve efficiency as well. Excuse me. Second one is supply air temperature reset. Supply air temperature, like what is the temperature of the conditioned air being supplied to the servers? If the servers, because traditionally in my experience, what I had seen was like they used to keep it very close to the dew point or just around 2 to 3 degrees higher than dew point. It used to be so cold inside the data center because anybody want to go to the data center, they has to wear some protective cooling because the technology was not had improved that much and there was no the concept of energy efficiency in data centers at some point of time. So with the increase in the energy prices and increasing awareness about energy efficiency, the supply temperature was started to increase because the electronics inside the servers can take an increased server, a raised server supply temperature, which was which did not make the server's performance to degrade in any way. So it was basically a mindset change or a behavioral change which happened, and which has a very huge impact on energy aspects of cooling because 1 degree increase in supply air temperature will increase the cooling efficiency by approximately 4 to 5%. So any raise in supply air temperature without affecting the server performance is a huge energy efficiency thing. Now, cable management. What happens is like when the most of the cooling still presently is supplied to the servers using raised floors, where the conditioned air from the unit is supplied through the panel, underground panel, and some uh, panels will be kept open for the at the server entrance level to get the supply air inside to the servers. Now, if that path is being blocked by cables or any other materials, then that supply, there will be some vortex created inside that supply air stream, and that will affect the supply air movement across the server racks. So basically, it is always better to have the server racks confined to the floor and such that the supply air stream will not be affected by it in any way. Next one. Second strategy is again free cooling, what we call it as economizers. See, this can be done only in places where the humidity levels are within the reasonable limit. This ASHRAE Technical Committee 9.9 recommends the maximum humidity should be around 60% for the airstream coming into the data center. So if the humidity level naturally is less than 60%, an airside economizer can be used to supply the outside air directly into the data centers with bypassing the mechanical cooling. This, as Srinivas sir was mentioning, this can happen in two possible scenarios. One during the winter months and one during the cooler evenings or cooling nights. When the outside air temperature is very low, and those air can be directly supplied into the data centers without mechanical cooling. This will have a huge impact on energy performance because once you bypass mechanical cooling, the energy used by compressors is completely bypassed or eliminated. That will be a very huge thing. There will be slight penalty in terms of fan energy, but that can be easily compensated. That is much less compared to the energy being saved in compressors. Similarly, on water side compressors, like again during the cooler months and during the cooler temperature hours, the water used inside the data center can be directly cooled using a cooling tower bypassing the chiller. So once that the cooling tower with the cooler outside air will be able to bring down the water temperature to such an extent that it will be able to cool the water to the required temperature by bypassing the mechanical cooling. So otherwise, these things can be used as a complement to the mechanical cooling as well, because the cooler supply temperature or cooler chilled water temperatures being supplied into the chiller, that will have the compressors need not work very hard to get the required cooling. So the free cooling is one of the major energy impactors. Of course, it is location based and also with is weather based. Next one, please. Now, what are the advanced coolings we have? As we discussed in the one, this is direct to chip cooling. This is liquid cooling. It's a part of direct to chip cooling is a part of liquid cooling, where the chilled water or the refrigerant is directly supplied to the rack level. It is and that with the chilled water, the server or the chip will be placed directly over a heat exchanger, what we call it as cold plate. So this method, it has a very good heat absorbing capability. It is used for very high performance computing and these days gamings and everything. So the cold plate here is directly mounted over the chip, and the refrigerant or chilled water is directly supplied over that, and that the cold plate will absorb the heat being generated by the either CPU or the servers. In that way, the cooling is achieved at the local level. Second one is like immersion cooling. As seen in the picture next to, the entire server is dipped in the liquid, and that liquid will absorb all the heat being generated. So here one is like benefits of this is like when it is having a very high server density, and it is these two methods are very much an recommended aspect, but this has some challenges as well, because anything once if a server gets any problem, then the entire unit needs to be switched off to get that one server out and all those things. But in direct to chip cooling, that problem does not arise, so that can be easily used over there. The last one is what is called as evaporative cooling. Evaporative cooling is basically like it is what a human, how the human perspiration works. The air passes directly through a wet medium like filter, but during this process, the air temperature decreases, but it also gains in humidity. So if the data center is in a place where the humidity levels are really low, this method works. But it also means like as the temperature decrease, it also adds humidity. So if the humidity control is very critical here. So the technology is very rarely used in data centers because the low humidity places are deserts and all. But some of those deserts like Dubai and all those places they use because their nightline temperatures are very low. So these they can use this kind of method where the required humidity can be achieved by properly controlling the supply, the air flow, and as well as the water temperature. Indirect evaporative cooling uses a heat exchanger where the air stream does not come in directly contact with the water medium, but it will reduce the temperature without affecting the humidity. So this is much more and of a better option compared to direct evaporative cooling. But again, these are very specific location specific. These are like actually like since this doesn't have any mechanical cooling, these are very energy efficient because there is no compressors used because it is mostly some fans and pumps. But again, one of the constraints we have in country like India is our water resources are also very much limited. So these are water intensive. So this is again can be used where there is abundance of water. Next one, please. This is how it's a graphical representation of direct and indirect evaporative cooling. Nothing much of what I just explained here. Now, future of cooling, as Srinivas sir was saying, AI and machine learning optimization is critical because one of the requirement of cooling is directly proportional to the load. So if the load determines the heat generation. So if the more we perfect the load prediction, more we perfect the heat generation, then we will be able to predict the cooling requirement as well. So that is one of the critical areas where Vigyanlabs is doing a lot of good work on that. And this also means with AI optimization, the cooling capacity can be adjusted, and each of these cooling units will have an optimum operational point. So more you operate around that operational point, it will be more efficient as well. So yes, this will be one of the future, and this is a lot of work is being done here. Then the heat is being generated. This heat reuse concept is now being very much used in Scandinavian countries like Norway and Sweden, where the heat generated from the servers are being used to are being absorbed into the water, and that hot water is being supplied to residential purposes for heating. So this is again a location specific. This happens in Scandinavia or where cold countries happen. So this is, but of course, it is a very novel concept which can be used where it is can be applicable. So what are the benefits of being efficiency, improving efficiency, and what and all we can get out of? Why do we need to put so much effort in being energy efficiency and all of things? One, as this is specific to India, basically because lot of energy markets are not commercially operated. It operated on lot of factors. One of them is politics. So with commercial energy rates being very high, reduced energy costs are one of the major these things for the companies. So being energy efficient and reducing the energy usage will reduce the operational expenditures as well. So lower the energy efficiency, higher the energy efficiency, lower will be electricity bills. And also like what happens is like being operating the equipment at its most efficient range will reduce the operation, will improve the the equipment life as well. So that will one of the, so in that context, it will reduce maintenance. So in both the reduced energy cost and reduced maintenance, your operational expenditure will be reduced. Secondly, your carbon footprint is reduced. So you become the company, and as an organization, you become more sustainable. Because see, being energy efficiency is not affecting your performance in any way. So it's increasing sustainability means like sustainability means you're reducing carbon footprint without affecting the performance. And being, as I mentioned, that being operating at the most efficient point, it improves the reliability of the equipment as well. So it won't lead to any breakdowns or anything unexpected breakdowns in it. That pretty much concludes my presentation. So I'll be happy to take any questions if there
Absolutely. Thank you
are.
so much, Narasimha. Very
Pleasure.
insightful. We do have a few questions. Okay.
Sure.
So first question, I think you kind of answered, but maybe elaborate further that heat reuse, right? Uh,
Uh-huh.
Obviously, we are taking out. I mean, there's a heat generation, and it's a desirable thing, and we are doing something to eliminate that. But can that be reused? We address that in Indian parlance. Anything can be done. In fact, the people ask that can that be used to heat our lunch boxes?
Heating lunch boxes, of course, are like say, let's take a place like Bangalore, a company like Google or anybody, if they have a data center there, how much ever small it is. So if they are using water-based cooling technologies for data centers, that water comes out warmer only. So that warm water can be like it can be reheated to an extra temperature to do some kind of like what you
Optimize.
put it in buffet trays and everything like that. Or or
Yes,
you can use it for restroom purposes as well, because so that is when it is heating water is there. Uh,
absolutely.
but if the water, if it is only used to the municipal water purpose, the municipal water,
Mhm.
and it is used continuously inside a closed loop, then you need to have some other then other mechanism to grab that heat. So it is
Absolutely.
possible. You can
Possible. Yeah.
lunch boxes may be a bit
Maybe
stretch here,
far-fetched,
but
but
it is
yeah, sure, absolutely.
when it's possible.
And there are a couple of more questions.
Sure.
So this is from Dr. Saravanan Raman. It's quite common as we experience in large-scale industrial cooling plant operated within the embedded control system with AI guidance. In
Mhm.
that case, how many safety checks that attract the provision of compliance to ensure the prevention of major hazards? So it's about safety checks, additional safety checks which we have to do uh,
Sure.
in order
So
to, yeah.
the safety checks means like actually one we need to always monitor is the humidity in the airstream coming into the data center. The dew point temperatures of that for that particular dry bulb and humidity ratio
Mhm.
should be sufficiently larger. Because
Right,
if the
right.
air stream goes towards the dew point, then it starts condensing. And how, if even at 60% recommended, also the the water droplets will start forming in that. So that
Agree.
may affect, that may create short circuit, that may create molds and all those things. So that is one safety check is like that one. We always have to monitor the relative humidity and dry bulb temperature coming in.
Absolutely.
Secondly, the integrity of the joints,
Right.
whether it is air joints or water or refrigerants, they have to be monitored always. And even with the minimal human occupancy inside the data centers, there will be carbon dioxide being generated. So there should be a way where that carbon dioxide needs to be captured. And also like the integrity of the joints, carbon dioxide monitoring, dew point, these are the safety checks that needs to be happening actually.
Absolutely.
Secondly, like on the electrical part of it, you should keep on monitoring the motors, like of the compressor
Mhm.
motors and all. If there is a power surge, if there is a unnecessary heating, especially inside the data center, all the servers are connected through panels. So you need to have a thermal gun and you should be monitored on a continuous basis whether there is any heating taking place inside those things, inside the panels. Because once there is heat, the sufficient heat accumulation inside those panels, the moment you open it when it comes in contact with the air, there will be fire. So the safety check is again on the electrical side is also very critical.
Very critical. Thank you, sir. There are a couple of more. Yeah. So one question I had was, as you recall, there's a ASHRAE, which is at the international level, and there's a ISHRAE, there's a
At the
India
Indian
level.
Yes.
So what are the pertinent standards which you have seen in your experience, vendors use or customers use, and are there any different from the international ones?
Not much, because ISHRAE, it's the way the base they start is from ASHRAE.
Okay.
So from ASHRAE only. So the basic principles, basic codes will be from ASHRAE itself. Only ISHRAE, what we will do, and they will be customize it to the Indian standards, Indian climatic conditions, Indian power quality ratios, and all those things. So ISHRAE has a guidelines for designing for data centers as well. So which is not a very far deviated from
Different from
ASHRAE
the
standards,
international one. Yes.
but it is like it has more to Indian standards.
Tailored for India.
Tailored Indian standards, because our power quality is different from here, and our voltage here is also like 440 volts, and the US uses 110 volts for single phase and everything. So that ISHRAE usually standardizes or localizes it to Indian portions.
Absolutely. We have one question for Srini as well in between. Let's bring Srini. If we could see you, Srini. Srinivas Varadarajan. Yeah.
Yeah.
So taking the same question, right? Are there any metrics around maximizing the device longevity, health, or end of life? And device could be, all the devices. And my additional anecdote would be, as you know, everybody, including NVIDIA and others, GPU will probably go end of life in next 2 years, right? I mean, of course, it'll continue to work, but the effectiveness or something new will come. So how do you kind of cope up with those aspects of it, and what additional precautions do you take into consideration?
Yeah, I think it's a couple of things, right? One is look at the manufacturer's warranties, right? Device. Okay, so one is what manufacturer end of life. Typically, servers come with 5 to 7 years, 5-year warranty, and you can probably extend, another 2 years, 1 or 2 years, right? 1 or 2 years lifetime. But I've seen just looked at, historically data centers. The number one common source of failure servers has been power supplies. Population to fail, fans fail, then dust. And the other thing is the disk, right? Hard disks. Now today we are eliminating magnetic hard disks, okay? Especially flash drives used to fail. Just eliminated. Next thing is fans, right? Is in our data center, I think we completed the 5th year. We haven't had a single failure. One of the important things is what I've seen is this, even though you say data center is clean, a small part of dust occurs, and then we have seen the fans getting dust, right? As long as you keep, so one of the things we've done is from day one, we put a PM 1.0 filter, sensors from day one. Make sure there's no dust particulate matter. So although it's invisible, Indian environment is some dust. People go in, say one is avoid people going inside and data center, coming in and out. Make sure there's no air leakages and all. Third thing, if you maintain the optimal, so first source of failure is power supply. Next, your memory dims, right? Moment you exceed the temperature, directly the dims fail, right? As long as you maintain the temperature envelope as per the recommendation of the OEM, right? In the fair temperature zone, you should never see this failing, right? It's 6-7 years your server should work. Any change from equipment. One is, even the server works. Do you have warranty or not, right? Because warranty aims, you need the OEM to support, upgrade firmware, and so on, right? Very often I think, as long as you maintain the optimal environmental, right? Temperature, cleanliness, dust particles clearly should last, as far as the life is concerned, should last for 6 to 7 years.
Yeah.
Next, you're coming to NVIDIA, right? NVIDIA are talking about, NVIDIA talks about only the training part, right? Training is one where you use a heavy, right? You use you run the training for weeks together. You pretty much run the GPUs at 100% full load, right? So those are the ones probably likely to wear out faster because it gets hot. As long as you maintain the temperature efficient, right? So there's operating range, right, for every equipment. As long as you maintain the proper cooling and temperature, humidity, right, controlling. I don't think you should see any failures in the equipment, right?
Understood. Thank you, Shri. And one more question from the audience is, in iron EC, how will cool water evaporate? Is there any low pressure applied to that?
The pressure variation will not be there. It will, all those things happens at the atmospheric pressure itself, but it will be counterflow. The water will, it is like pretty much like a cooling tower, like where the water being sprayed from the top and the hot air will be pumped outside, pumped up. So when they come in contact with each other, the water absorbs the heat, and in that this thing during that moment it will evaporate because of the higher temperature of the airstream. So in the indirect evaporative cooling is like there are two airstreams. One is the primary airstream, and the other one is secondary airstream. Secondary airstream is the one which gets cooled by the direct contact with water, and that cooled air will in turn cool the primary airstream. So like it is not exactly, there will be a pumping for the water and there will be a suction of the air from the uh, top side, but usually the heat transfer takes place within the ambient temperature, ambient pressure itself.
Understood. Good, good. Thank you. Sri, we have a couple of more questions. One is, going back to your initial, opening conversation, right? Whether it is an inverse of the hyperscaler. Could you just talk about some of the use cases, both AI as well as non-AI? And secondly, also the gamut of clients you have seen. Are they specific to government, or have you seen that need even in the non-government sector? So if you could just talk about that based on the clients or the customers which you see in the last 1 year or so.
I think I have seen a wide range of customers. One AI, right? Today, if you look at today, AI, only the small percentage, right, of the people who build the models, they do training. Majority, 99.99% will end up doing inference, right? And there are many use cases coming in the inference where they need a sub-second response time, right? Sub-second response time. And I guess example, speech to text, local languages. You can't have 3 seconds. Real time, you want to do speech to text, right? You don't need 2-3 seconds, is a lag, right? You need a sub-second, 50 millisecond, 100 millisecond response time is required. Speech to text is one. And look at Industry 4.0. Basically, you have plant and machinery running. You can't afford latency, right? You need a real time response. You need an edge. Third use case is that, basically people wanted to, keep, I've seen in defense and other, special industries, right, where they want confidential data. They want to keep on-prem. So far, it was proved that, having a small data center was not economically viable. So with this use case, fits the model where you can actually have a small data center on-prem. People want a private cloud on-prem, which is fairly economical and doesn't cost it's very economical to run. You don't need a large data centers. These are the sort of three kind of use cases we're seeing right now.
Both in the government as well as the non-government,
Non-government,
AI, non-AI
yes,
scenarios, right?
Because AI coming in, what's happening is people are figuring out that then the model, they want to host the model themselves, because you train the model while inferring, there's this sort of ongoing training happening to the model, right? They want to keep the model private to them because the model is IP, right? People realize that using a generic model doesn't help them. They need to do SLMs. They want to train the model further, and they want to keep the inference data with themselves, right? They don't want to share the data. That's why people want to keep the AI in on-prem, right?
Correct. And even in our experience, what we have seen is whether it's a RAG or a fine-tuning would require more resources, while the RAG typical may not require a lot of resources, right?
Yes, that's right.
Yeah. Okay, cool. So absolutely fascinating to talk to both of you, Srinivas and Narasimhan. A lot of learning for me individually, and I'm sure the audience is going to take away a lot of key messages. And over to you, Dr. Sushila, for any last messages.
Thank you very much. I think today was a very important session. There is AI everywhere, all around us, coming more and more into our lives. Not just AI, but technology, information technology as a whole. All of which means, of course, there is a lot more that is happening with information and data. our data centers are becoming an extremely important center where there is also a lot of power consumption and so on. We're told that training a large model would consume about 700 kiloliters of water. That's a lot of water. A single query can drink up half a liter of water, more than any of us can drink in a single sitting. So this, therefore, as we adopt more and more of AI and technology, talking about this and looking for ways around optimizing all of this and around how we can kind of conserve what we can of the environment, whatever we've left of it, what can we do for it is a very, very important discussion. So
very, very timely.
yeah. So I really want to thank both Srinivas and Narasimha for taking time to come here and do this for us, and Nitin, to you for having moderated this in a very interesting way. So thank you all. What we saw today was the passionate work of two technology leaders who've taken it upon themselves to look at innovations that will help reduce the carbon footprint of IT and AI. And in our first presentation, Srinivas Varadarajan talked about sustainable energy at the last mile and talked about why this whole concept of a small data center, micro data center is so important. We looked at three areas. We looked at the physical data center, we looked at the equipment inside it, and we looked at the various systems around all of that. The elements of a data center are today managed as silos, thought about and designed and operated as silos. And he highlighted the reason why we need to look at more of integration and managing it all together. There are several innovations that he has designed and implemented. Very, very importantly, he's implemented them, which includes the physical building itself. And it was very fascinating to listen to you say that you looked at specially designed bricks. That is, and also looking back at traditional materials and seeing how those can be brought in to design buildings that are more energy efficient. Dropping things like the false ceiling, no one knows why they are there, and a lot of automation, and very fascinatingly using the same technologies that we are talking about, doing many other things, but do homework and so on. This is probably a much better application of AI itself. The manner in which the various systems are integrated and managed together, including identifying energy leakages, phase balancing of power, thermal load modeling so that cooling can be optimized and controlled suitably, and so on. We then focused on cooling itself, which is obviously very important since the single largest hogger of energy in a data center is just cooling. 30 to 40% is the single largest chunk. We learned a lot about the different types of cooling that are in play today: airflow management, liquid cooling, etc., etc. But the most important message from this was choose a method of cooling that is appropriate to the specific situation that you are in, the environment that you are in, etc. So today we've seen some really nice innovations, and I'm very proud that IITACB has had the opportunity to host and showcase this work. We wish you the best and hope that this will multiply and be applied in more and more places. So thank you very much. And to our audience, thank you for all your questions and interaction. It's a very important part of our webinars. So thank you all very much, Srini, Narasimha, and Nitin. Bye.
Thank you so much. Yeah.
Thank you.
Bye.
Thank you.
All right. Thank you.
Thank you.